Let's talk about digital electronics. Digital electronics is extremely important for mechatronic systems. Not only we use microcontrollers and microprocessors to control our mechatronic systems and robots, we also use digital gates to create input and output circuits for signal conditioning. Digital electronics is built around digital signals. A digital signal is a discrete signal that has only two possible values, a high and a low. We might also use the terminology a logic 1 or a logic 0. These two values, they are voltage levels. If it is a 5 volt based system, then a logic high might represent 5 volts and a logic low might represent a 0 volts. As you would see over here in this picture, logic levels are actually not specific voltages, they are a voltage range. So these two pictures over here, they are for the CMOS based digital systems. And for a CMOS based system, the input signal level, logic high, is considered anywhere between 3.5 volts and 5 volts. And a logic low is considered between 0 volts and 1.5 volts. On the other hand, for the output signals, we are a lot more stringent. This is the signal that is coming out of a digital gate. So we have a lot more control on what voltage level we can output. So it is a lot more stringent, and you can see that a logic high will be considered a high only if it is 4.95, between 4.95 and 5 volts, and it would be considered a logic low if it is between 0 and 0.05 volts. Now, we are a little bit more forgiving on the input side here because there might be some line losses as the signal progresses through the system. So we have to be a little bit more forgiving for that. To understand the digital electronics, we have to talk about the binary number system. Binary number system has only two digits in this system, a 0 and a 1. But before we talk about binary number system, let's talk about a number system we are more familiar with, and that is a decimal number system, which we are taught from the early childhood. So a decimal number system, we have 10 digits, and those digits are from 0 to 9, and that's why we call it a decimal number system. Now, let's say if I pick a decimal number that has 3 digits and I just write them down, intuitively you know that this number, the value of this number is 123. Why is the value of this number 123? Well, the reason is that each of the positions in this number system is assigned a certain value, that is the place value of that position. So this over here is my unit, this over here is my tens, and this over here is my hundreds. So that means that my unit over here, the value of this position is 1, value of the tens is 10, and 100 is the value of this third position to the left. Now compute the total value of this number that has these 3 digits in this specific order. I'm gonna multiply the place value with the digit. So 1 times 3 plus 10 times 2 plus 100 times 1. And then I add them up, and that gives me 123. That's how I know the value of this is 123. Now, if we write these place values in terms of the power of 10, I can write this over here, 10 raised to power 0, which gives me 1, 10 raised to power 1, 10 raised to power 2. And then I can say that, okay, this over here is my position 0, this here is my position 1, this here is my position 2. So that gives me an easy way to figure out what is the value of that position. Now let's write a binary number 0, 1, 1, 1, 1, 0, 1, 1. This is an 8-bit binary number. Why 8-bit? Because each position is a bit. and a bit can have only a value of either 0 or a 1, and if we count this, these are 8 bits, so it's an 8-bit binary number. Now if we go by the same concepts that we developed over here for the decimal system, then that means that this is my bit position 0, bit position 1, 2, 3, 4, 5, 6, and 7. That means the value for this bit position over here, since my number system is a binary number system which is base 2, that means the value over here is going to be 2 raised to power 0, and the value of this next bit over here is going to be 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, 6, and 2 raised to power 7. Now I'm gonna multiply each of this and then sum them up to get the value of this binary number in decimal. So it is going to be 2 raised to power 0 times 1, which is my first bit over here, times 1 and sum them up, times 0 and then sum it up, and times 1, sum it up, times 1, sum it up, times 1, times 1, and times 0. So if I evaluate this expression, 2 raised to power 0 is 1 times 1 gives me a 1, plus 2 raised to power 1 is a 2, then 2 raised to power 2 is a 4, but it multiplies with 0, so I get a 0, plus 8, plus 16, plus 32, plus 64, and then plus a 0 over here because we are multiplying it with a 0. If I add this up, so 64 plus 32 is 96. 96 plus 16 is 112, plus 120 plus 2 plus 1, 123. So this gives me 123 in base 10. So we use a subscript to denote the base of the number. So over here, this number I can subscript either a number 2 over here, or I can put a B over here to denote that this is a binary number. Now in this binary number over here, we can clearly see that the rightmost bit position has the least value. It is going to be always the value of either 0 or a 1 when we evaluate it. So this over here is called my LSB, least significant bit, and the value of my leftmost, the place value of my leftmost bit is always going to be the most. So that is called my most significant bit. Now we use this place value technique to convert our binary number into our decimal number. To convert a given decimal number to a binary number, we use a technique called successive division. We divide our decimal number. So let's say my decimal number is 123. We divide it by the base to which we want to convert it to. So in this case, we want to convert it into a binary number. So we divide it by 2 successively until our quotient and the remainder is 0. So over here I have 123. If I divide it by 2, my quotient over here is going to be 2 times 6 is 12, 2 times 1 is 2, and I have a remainder of 1. Divided by 2 again, and 30 times 2 is 60, remainder of 1. Divided by 2 again, 15 times 2 is 30, and remainder is 0 now. Divided by 2 again, 2 times 7 is 14, remainder is 1. Divided by 2 again, 2 times 3 is 6, remainder is 1. Divided by 2 again, 2 times 1 is 2, remainder is 1. And divide by 2 again, and since 1 cannot be divided by 2, so my quotient is going to be 0 and my remainder is going to be 1. So if I divide this by 2 again, of course I will get a 0 over here. So now I can write this into my binary numbers starting from the very bottom and going to the top, and then I will write it as 0 1 1 1 1011. So we get back our number in the binary number system. So 123 in base 10 gets converted into 011 1011 in base 2. Now keep in mind this is called a natural binary number. Natural binary number. All right. Okay, so this binary number over here, it's very hard to actually read this number. So bit by bit. So what we do is we use a byte. A byte is an 8-bit binary number. So this here is my 1 byte. Then I have my nibble. Nibble is my 4 bits, so it is a half byte. So this here is going to be my nibble. And I have word, which is going to be 2 bytes. In other words, it is going to be 16 bits. And then I have double word, which is going to be 4 bytes, or 32 bits. Another number system that we often work in digital electronics is hexadecimal system. In hexadecimal system, the base is 16 and my basic digits are 0 to 9, 10 digits, then A, B, C, D, E, and F. I can convert my decimal 123 into hexadecimal by using the successive division again. So I'm gonna divide 123 by 16 this time. So 123 divided by 16, my quotient is going to be 7 and my remainder is going to be 11, because 16 times 7 is 112 plus 11 gives me 123. If I look at my digits in my hexadecimal, 11 is actually a B. So that means that I will write it as a B. If I divide it again by 16, my quotient is going to be 0 and then my remainder is going to be 7. And using the same technique over here, I can now write it as my base 16 number, which is 7B, or 7B and hex. So essentially 123 in base 10 is equal to 0111 in base 2, which is equal to 7B in hexadecimal or base 16. I can create a mapping between my hexadecimal and decimal numbers. Then let's write the equivalent decimal values for this. So up to 9, it is going to be the exact same value. And A is going to be my 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Now I can go ahead and create a mapping for the binary as well, and that's where the value of hexadecimal number shows up. So if I want to write binary number for each of these hex numbers, I have to decide how many bits I want to use. If I use only 1 bit, I can have either a value of 0 or a value of 1. That means I can have only 2 values. If I use 2 bits, then I can have 4 possible combinations, and those 4 possible combinations would be 00, 01, 10, and 11. If I use 3 bits, it's going to be 8 possible combinations. If I use 4 bits, it is going to be 16 possible combinations. That means that if I want to write an equivalent for each of these hexadecimal digits, I need to use 4 bits. So I'm gonna go ahead and start with my 0 over here. So it is going to be 4 zeros, 4 0 bits. Then I have 0001, 0010, and then 0011. 4 is going to be 0100, 5 is going to be 0101, 6 is going to be 0110, 7 is going to be 0, 1, 1, 1. And this is my halfway point. And see the transition from here onwards. So next is going to be 1, 8 is going to be 1, 0, 0, 0. See this here, my most significant bit is 0, and rest 3 bits are 0. Over here, most significant bit is 1, rest 3 bits are 0. And you will see that this pattern is going to repeat. So my 9 is going to be 1, 0, 0, 1. 10 is going to be 1, 0, 1, 0. 11 is going to be 1, 0, 1, 1. 12 is going to be 1, 1, 0, 0. 13 is going to be 1, 1, 0, 1. 14 is going to be 1, 1, 1, 0. And 15 is going to be 1, 1, 1, 1. Later on, I'll explain how to write this table in a little bit more easier than just from your memory. Now, the benefit of hexadecimal and binary number system, understanding both of those, is it becomes very clear when you convert between hexadecimal and binary number systems. So let's say we are working with this binary number system over here. So this is 0, 1, 1, 1, and 1, 0, 1, 1. So if I group them into 4 bits, starting from my rightmost bit, this is a group of 4 here, this is a group of 4 here, and I simply write a direct mapped value of each of these two digits, I get my hexadecimal. So I can see 1011, which is this digit over here, that is going to be my B. So this here is my B. And this one here, 0110, that is going to be my, so 0110 is this number over here. That is going to be my 7. So I have 7B. So it's a direct conversion between my hexadecimal and my binary number system. However, it is a lot easier to read a hexadecimal system as compared to a binary number system. You may be wondering, how did we get all of these values in this table? We can actually use successive division to get these values. So let's say I want to find out what would be the binary value for D in hex. I know D in hex is 13 in decimal. So I'll start with 13. So 13 in decimal, and I'll use my successive division on it to find the binary from it. So divided by 2, 2 times 6 is 12, remainder is 1, 2 times 3 is 6, remainder is 0, 2 times 1 is 2, remainder is 1, and if I divide by 2 one more time, my quotient is going to be 0 and my remainder is going to be 1. And now if I write it from bottom to top, my value is going to be equal to 1, 1, 0, 1 in base 2.